Today we're going to talk a little bit about measurements in quantum mechanics. Specifically, how do we interpret the measurements that we perform? What information do they give us? And how do we quantify our expectations of a particular measurement? Let's start with a good old Stern-Gerlach device as part of our measurement apparatus, where we're going to take some state, representing a particle, an electron. We're going to send it through our Stern-Gerlach device, and we're going to measure whether it is spin up or spin down along the orientation axis of our magnetic field. Let's say we run this experiment. We send an electron through our Stern-Gerlach device, and we find a detection at the top position, which indicates that the particle has spin in the positive x direction. What does this tell us about the initial state of our particle psi? It doesn't tell us very much. It tells us that there is a probability amplitude of psi to have spin in the plus x direction, but it doesn't really tell us its value or its phase or any information about it at all, other than that it's not zero. I've only done the experiment once, right? So remember, our experiments in quantum mechanics are probabilistic, or the behaviors or the properties of quantum mechanical systems are probabilistic. So how do I learn more information about the state psi? A naive idea could be to say, okay, well, why don't I just take my electron and do it again? Let me take the same electron and let me send it through another Stern-Gerlach device oriented in the x direction, and let's measure the spin again. If I did that, though, I would once again get exactly the same result. Because once my particle is detected over here, it is no longer in the state psi, but it is now in the state x plus. So if I want to learn more information about psi itself, I want to know what was the state of the electron before I made this measurement. The only way I can do this is statistically. What I have to do is I have to create multiple electrons in the same state as each other. You might think, well, if I don't know what the state was to begin with, how could I possibly make sure I have a whole bunch of electrons that are in the same state as each other? Well, one way I could do that is I could use a measurement like a Stern-Gerlach apparatus. If I place a whole bunch of particles and I only take the ones that come out of the top here, I am selecting only the particles that have 100% chance of being in the x plus state. So that's one way that I could actually select or prepare particles to have a particular state. Now, this is not particularly interesting. If I do that, what's the point of measuring it? If I'm only selecting the particles here, I already know which states I've selected. I've selected the states that look like this. It turns out that in nature, and certainly in our experiments, there are phenomena that actually produce consistent quantum states. An example from nature would be some forms of radioactive decay. If you get a whole bunch of identical radioactive elements and you measure their decay products will actually be in the same state every time. So that's a natural example. In an experiment, we can induce all kinds of funny behaviors by exposing atoms or molecules to electric and magnetic fields or hitting them with photons, and we can do fancy things in order to produce a consistent state. So it is actually possible to produce a whole bunch of identical states to each other without knowing what that particular state is. But again, that's important because if I just run the experiment once, I say, okay, well, it was this. The only information that tells me is that it had a non-zero probability amplitude corresponding to the x plus state. But it doesn't tell me what it was. It doesn't tell me that anything about the amplitude in the x minus state other than that it was not a unit amplitude. It doesn't have a magnitude of 1. So if I want to learn more information, I have to send multiple identical states through one after the other. So each time I can say, all right, this time I got spin up in the x direction. I got x plus. I got x plus again. I got x plus again. This time I got x minus. This time I got x minus, x plus, x minus, x plus, x minus, x minus, x minus, x plus, x plus, x plus, x plus, x minus, and so on. And if I do this very, 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 very many times, eventually I will approach a consistent ratio between the two. And that's the only way to really determine the information about this initial state. It's to produce many identical such particles and to run the experiment many times to tally up the results of every one of our experiment and see what it's trending towards. The more times I run the experiment, the more statistically significant my results will be. If I run the experiment once, I basically know nothing. If I run it twice, I know a little bit more. But if I run it 1,000 times, I know a lot more. If I run it 10,000 times, I know a lot more, and so on. This is fairly standard statistics, and this general process is crucial to any scientific endeavor. But the details of what we're doing here is subtly different than what we do in most sciences, and certainly in most classical physical sciences. For example, let's imagine you have a box that launches frisbees. And there are different settings of the box, and depending on the setting, it will spin the frisbee in different ways. Maybe the frisbee will be oriented horizontally and spinning clockwise, or maybe it'll be spinning counterclockwise, or maybe it can be oriented vertically. And the setting is determined by the manufacturer, and you have no way of actually looking at the setting without actually running the device. So how would you determine the particular setting of the box? Well, you could perform the experiment many, many times. If you do it once, in this case, you'll probably be pretty sure that you have the answer. In other words, when I shoot out a frisbee, well, maybe it's spinning counterclockwise while oriented horizontally. Well, I just observed that. I made an observation, and that observation corresponds to the state of the frisbee, how it was launched in the device. So the state that you measure corresponds directly with the state that you had. If I perform the experiment many times, if the device is well constructed, I will get the same result every time. Again, if I want to be really sure if this is life or death, I need to make 100% sure that this box shoots out frisbees horizontally and spinning clockwise. I'm probably going to test it more than once just to make sure. Maybe I made a measurement error, or maybe the device isn't perfect and it doesn't do the same thing every time. So I would do it more than once to be sure. And by doing it more than once, what I'm doing is I'm improving my statistics. So I have a better idea of the behavior of this box. It allows me to quantify what is the expected result and how much does it tend to deviate from that expected result. For example, maybe it wobbles sometimes, or maybe it comes out as a slight angle sometimes and it's not perfect. Maybe once out of every 100 times, something happens and it comes out vertically instead, or it's spinning the opposite direction. But those have to do with the imperfection of the device that spins the frisbee. No matter what, if my particle leaves this box spinning counterclockwise, then it means it was spun counterclockwise in the box. Well, our initial state psi is like our box. The difference is that when I get my measurement in the end, in quantum mechanics, my measurement doesn't tell me what was happening inside of the box. Whereas in classical mechanics, how the frisbee comes out of the box tells me what happened inside of the box. It was spun in that direction. So this was done to it. So there is a distinction here, because in classical mechanics and classical physics and in science, we usually use statistics to just be more confident that the result we observed is what was actually the case. In quantum mechanics, we have to use statistics in order to arrive at a result in the first place. My result is I want to know what the state psi is. In order to figure out what that state was, I need to do the experiment many, many, many times. Whereas each individual measurement of our frisbee tells us what the state of that frisbee was for sure. Each individual measurement of our electron tells me a little piece of information about what the state of that electron was. Let's talk about a specific example. Let's say we do this. We take a whole bunch of identically prepared electrons and we send them through our Stern-Gerlach device oriented in the x direction 1,000 times, and we find that 1 out of every 4 times we find that it has plus h bar over 2 spin in the x direction, and 3 out of every 4 times it has minus h bar over 2 spin. So what information does that tell us? Well, it tells us the probabilities, obviously, but it also tells us the magnitudes of the corresponding probability amplitudes. It doesn't tell us anything about their phase. It doesn't tell us whether they're imaginary or real or somewhere in between. All it tells us is that the amplitudes have magnitudes of 1/2 in the square root of 3 over 2. So we can write the actual amplitudes as their magnitudes times e to the power of I times an angle. A different angle for each one, independent of each other. And the experiment we have just performed, even though we ran it many times to get these probabilities, tells us nothing about those phase angles. So at this point, our best representation of the initial state, psi, is this. If we want to learn more information about the values of these angles, we can learn more. We cannot learn everything, as I've mentioned before, but we can learn something. The easiest way to do that is to perform a different set of experiments, this time measuring the state in a different axis. For example, maybe when we measure the spin in the z direction, we get a 50-50 split. In that case, the magnitudes of the probability amplitudes in the plus and minus z directions have to be 1 over the square root of 2. To make use of this information, we can always express x plus and x minus in the z plus and z minus basis. That will give us an expression for our initial state psi in terms of the z plus and z minus states. Then we can apply these restrictions, and that will actually tell us a lot of information. It'll allow us to get rid of one, but not both of these angles. In order to simplify this math a little bit, it's actually really convenient to factor out one of these angles. So we can do that. We can factor out, in this case, we can factor out the 1/2 as well. So I'm going to factor out 1/2 e to the I theta plus, and that's going to give us z plus the square root of 3 e to the I theta minus divided by e to the I theta plus times x minus. I'm sorry, this should be an x plus. This term over here, we can simplify it to represent it as a difference between the two angles, like this. And what I'm going to do is I'm going to redefine my angles. I'm going to write theta plus. I'm just going to write as theta naught. And I'm going to write theta minus theta plus as theta. Just to simplify notation going forwards. And so this gives us the expression 1/2 e to the I theta naught times our state x plus the square root of 3 times e to the I theta x minus. And the reason why I'm doing that is because I have foreknowledge that it's going to be easy to find out what theta is, and it's going to be challenging. In fact, it's going to be impossible to find out what theta naught is. Using the probabilities that I outlined above and expressing our states x plus and x minus in terms of the z basis will allow you to conclude that e to the I theta must be equal to plus or minus I. Any other value of e to the I theta would give you an incorrect magnitude or amplitude for the measurements performed in the z direction. You'll actually be doing this as part of your homework assignment to prove that this is the case. Now, you might ask, okay, well, plus or minus, I still don't know what it is. If you want to figure out whether it's positive or minus, you would then have to perform a third experiment by measuring the spin of our state along the y-axis. Note that none of these experiments will tell us what theta naught is. In the end, theta naught will always show up in our results, in our experimental results, as a magnitude squared, and e to the I theta naught has a magnitude of 1. And so it will never actually contribute anything to our result. Again, the results of our experiments are probabilities. They don't tell us anything other than probabilities. We can then infer information about the amplitudes of our states, like we did over here. But all of that is inference based off of probabilities. And an overall factor of a complex number with a magnitude of 1 will never affect a probability calculation, because to find the probability, we are always taking the magnitude squared of a number. And so in the end, a piece of that number that itself has a magnitude of 1 is not going to have any noticeable effect in any experiment we ever do. And so we say that measurements in quantum mechanics can only be determined up to an overall phase. I can take any state psi, multiply it by e to the I times any angle theta, and there will be no measurable differences between those states. And so this is simply a feature of our mathematical model of the system. Is it telling us anything physical about the system, that there are an infinite number of states that are indistinguishable to us? Or that maybe this is just simply a mathematical artifact? Who knows? In this video, we learn how to determine as much as possible about a quantum mechanical state from a series of measurements. In the next video, we'll kind of do the opposite. If I know what my state is, what are some different ways that I can represent my expectations of the results of an experiment if I choose to run one?